So welcome to my presentation. I'm going to be presenting this paper that I found on ACM. It's a peer-reviewed journal, and basically the paper title is Towards a Rust-like Borrow Checker for C. If you want to see it, you can find it on this website, and this is what the paper looks like. And alright, let's get started. You'll notice that I have some graphics where these are the pragmas that I'll get into from the paper. But also, the main thing is that it borrows a lot of ideas from C++ and Rust for C. And I'm excited to talk about this because I'm very passionate about C code in general. I think C is actually my favorite language out of every programming language. But yeah, let's get into it. Alright, so let's explain the problem. So why not just rewrite C and Rust, which is the big meme that everyone likes to talk about. So the main thing is that the whole world basically depends on C. Now, if we look at the Linux kernel, most operating systems, most things, you look at some files that how do they handle plain audio? They end up calling a C library. How do you do anything in Linux? Everything is made through libc. That's how you talk to the operating system. Um, and so everything is used in C, and as such, companies they have legacy code bases in C, and with C, it has a lot of the opposite of guardrails. You can shoot yourself in the foot by doing pointer arithmetic, use after free, a lot of things are undefined behavior. And currently, or at least before this paper, the main things that they had was basically to switch the programming language, or to use some extensions of the C programming language, or to use this tool to convert C into Rust. Um, Now, they wanted to make a new solution because, number one, switching the language a lot of time for these companies or people who don't are short on time is kind of unrealistic for them. The use of C compiler extensions and dialects, a lot of the time these are not compatible with existing hardwares, and sometimes you need trusted compilers. So, one of the big issues actually with Rust is that if you look at Ken Thompson's on Trusting Trust, there's actually a lot of compiler exploits where you can basically inject code with the untrusted compiler. And C is one of the old compilers where basically it's very thoroughly read and reviewed, and um, they want to have the goal of basically having all these nice features of RAI like in C++ and in Rust, and borrow checking and memory safety in Rust, but with working in the bounds of a C compiler. And how do they achieve this? They basically have some source to source pipeline. So basically how this works is they have the source code, but what they do is they add these pragmas. So we're going to see more of these pragmas, but all of this fits within the bounds and the syntax of existing C. And so basically they have annotated C. Then the static analyzer can read the source code, and then when it sees the annotated C, it can analyze the lifetimes and the borrow checking of the source code, and then it can insert the things that it needs to do so that it behaves basically like a compiler where it changes your source code to be a little bit different. It's kind of in the same vein as like a C++ compiler doing adding in complicated stuff with like zero cost abstractions. Anyways, um, there's a couple of different ways that they achieve this. The main thing that they do is they have to make the C source code friendlier for the analyzer. So maybe for a human, this might be pretty easy to understand. Like if this function result plus this function result is greater than 10, then it doesn't work. But the problem is that for computers, this is pretty hard to understand because it's doing a lot of work on the if statement where it has to do a lot of computation. You see this a lot in Rust where they design patterns are basically they have to declare the variables, and then they do the if statements or the for loops or whatever. To make it easier for the analyzer, they basically break this up into all of these statements so that there's no computation happening in the if statement or the for loops basically. So this turns into all ternaries turn into if else, which I actually personally like. I'm not really a big fan of ternaries. Um, Most for loops basically become into while loops, and then um, for function calls, you basically always want to have them into some temporary variable, which makes it easier to debug. And then now let's talk about pragmas. So this is a thing in C that is a compiler directive, and so basically we can define this thing Coral, which is the name of their static analyzer or their new syntax, and they have a bunch of declarations for move and drop file. So an example here is we have pragma Coral, and if you want to make a struct have a move component, so that when we make something equal to something like an assignment operator, you can give it um, like semantics like, oh, this is a when you do equivalence with this, then it's going to move it instead of making a copy. In normal C, this is actually like impossible to do. Like you have to do in C++ with standard move. Um, and with the pragma, this is how it works basically. Um, Now you'll notice there is drop and drop file for this file. Basically, we can basically say that um, this will have a when it goes out of scope, it's going to clean up its own memory. And since it's specifically a file, then basically it's going to do the file close, like fp.close or fclose fp. So this slide is basically talking more about the ownership. So I mentioned before about the move and the drop, but they basically instead of making a copy of A by declaring B, we can basically say that we're moving the data into B, and that when we actually do this move, this is very important. A becomes invalid. So when this happens, and let's say we use A after it's being currently owned by B, the static analyzer can actually check it and give a warning at compile time. So it prevents double freeze and two owners. Now for more about the drops, this is an example of how with the annotated code, the analyzer can transform the source code into basically adding the drop file. In real code, it would actually be like fclose after this goes out of scope, but it's really cool because it's essentially achieving RAII. The resource acquisition is resource allocation. I think the acronym is escaping me at this moment, but basically it's the concept that when resources go out of scope, they clean up their own memory, and I believe it's resource acquisition is initialization is the full acronym. Anyways, they achieve this by having flags so that this also works in branches. So say we had some flag where we have this variable nd. Um, if the value is greater than 5, then nd becomes moved away. But if it's not, then um, it will probably be dropped. Now this is kind of a problem because at compile time you can't really tell if nd is going to be moved or if it's going to be barred or not. So what it does is how it achieves it is basically there's a flag that basically sets it to 0. So in the actual paper, it's going to be like underscore underscore nd dropped. Um, but by setting the flags on these things to 0, we can tell if it's still being barred or not. Um, Now in this thing as well, they also have lifetimes. So in C, there's very annoying errors where you can get dangling pointers, and it basically happens where the lifetime of something um, goes out of scope and you try to use it again. Um, so they kind of get inspiration from Rust, where you can basically enforce that the parameter and the return need to have the same lifetime. So as you can see in this graphic, we need to have basically x have the same lifetime as whatever the return value be over here. So by doing this, you can actually define the lifetimes to be basically the same. They achieve this by doing this percent syntax. It's a little bit confusing, but they had their own reasons for it in the paper. Um, Another example of this is basically if you have some function that has get max, where you want to get which one's bigger, A or B. Um, you need to know maybe the lifetime of A and B might be a little bit different. But at the very minimum, the return type of this constant has to be the same lifetime of A or B. So um, in the annotated code and the output that you get, it basically enforces that the lifetime of A and B are going to be as big as the result lifetime, as you can see here. And now we'll look at the results. So this is the table from the paper. And then I just put some bars to make it more readable. But basically, they had some testing suite over some 287 of total functions. And what they found is that a lot of the features, a lot of these functions were ignored because they weren't really supported in their implementation. But out of the ones that were not ignored, 82 were passed and 18 were failed. Um, Maybe the testing suite they had was not sufficient, but um, when they looked at the ones that they did use, only 40% of the functions had pointers, and most of the failure had basically pointer arithmetic and pointer functions. Um, in total, for doing all of these functions, it took them about 75 seconds. So it does add a little bit more cost to like the compile time of C, but um, in some cases, one might think that it's pretty much worth it for squashing all of these memory related bugs and basically having more readable C code. Um, and that's about it for the results. So, in conclusion, this is the, if I go back to the name of the paper, towards a Rust-like borrow checker in C. And I think it's very refreshing and very exciting. I like how um, it borrows a lot of the ideas from Rust and C++ into C in a way that it's compatible completely um, within C syntax at the very least. Um, it does RAI and has a lot of the basically has a borrow checker within C, which is kind of unheard of. And um, when it comes to non-lexical lifetimes, that's just referring to the algorithm that it does. In Rust, it does non-lexical lifetimes for borrow checking, which is the algorithm for borrow checking. The only cons I would say is that for the results, we kind of saw that a lot of them were ignored, and the things that you would usually use C for, which is like pointer arithmetic, and all of that power basically turns into being like unsupported, or it's not going to work in this kind of paradigm of thinking. It's the same thing kind of thing like in Rust, where if it's harder to basically wrap values around from the end back to the start with arithmetic and all that stuff. It also makes your C code a bit more verbose, but in my opinion, I kind of like this, but maybe some C programmers are not very used to this style of programming. And also you have to do the manual lifetime of annotations like we saw in this part, which I think was kind of complicated, but that's about it. Yeah.